Continuing our journey in Chapter 10, now we're going to talk about properties of liquids and phase transitions. And so, learning outcomes, expectations, feel free to pause and read through those. Yeah, so our journey starts in 10.2. We're talking about properties of liquids. And so previously we talked about, taking Lewis structures, assigning those structures based on VSEPR, and then talking about the molecules being polar or nonpolar or ionic, and then talking about interactions where there's ion dipole, which is the strongest, and then instantaneous induced dipole is the weakest. And so if we walk through that journey, the whole reason we do any of this process, from molecular formulas to assigning the intermolecular forces to estimating their relative strength, is ultimately because we want to predict properties, right? That's what we do in the sciences. We want to understand a system well enough to predict it and ultimately use that prediction to utilize it for some ends that we want to justify. And so we're going to try to predict properties based on these intermolecular forces. And so take from a molecular formula to actually compare different molecular formulas and make a prediction about their properties. And so in this first part of this chapter, we're going to talk about viscosity and surface tension, two properties of liquids. And so viscosity, pretty much everyone's at least conceptually familiar with the idea of viscosity, right? It's everything from commercials to what you use while cooking. Viscosity is formally the thickness of a liquid. Like, how much does it resist flowing? Is it fast? Is it slow? That's what we're talking about when we talk about viscosity. Interestingly, the units on viscosity are Newton seconds per meter squared, which is kind of interesting to think about. But when you break it down to beyond the bulk liquid, to actually thinking about molecules, essentially what has to happen is molecules have to move past each other. And so ultimately, this motion of molecules is going to be entirely dictated by how they interact with each other, also known as intermolecular forces. And so you have to separate these molecules, you have to get these molecules to move past each other so they can flow out of a container and ultimately and make a pool of solution. And so viscosity is directly dictated by intermolecular forces. How strongly do these molecules interact with each other? So the stronger the intermolecular forces, the higher the viscosity, the slower the flow of that liquid will be. Another thing to note is viscosity is temperature dependent. And so the higher the temperature, the more you can break those intermolecular interactions, the intermolecular forces decrease or they're broken, and ultimately the viscosity of the solution decreases. And so it really all ties together when you think about it on a molecular level. How strongly do these molecules interact, and what factors influence that interaction? And so an example would be heating up honey. You can get it to flow faster. The other thing to think about, as we talked about previously, molecular size matters, right? Size dictates the strength of the intermolecular forces. It also dictates how much they can tumble past each other, and also dictate the viscosity. So the bigger the molecules, the higher the viscosity of the solution. And so you can compare things like gasoline and wax. Both are hydrocarbons, meaning they're just made out of hydrogen and carbon. Gasoline is C8H18. Wax is typically C20H42 or greater. And so bigger molecules, stronger intermolecular forces, the molecular size is much higher. The intermolecular forces are stronger, it's much less likely to flow. And so again, we all have kind of a concept of this, but here's just showing low viscosity, things are going to pour very quickly. High viscosity, they're not going to move at all, even over a long period of time. And so again, you can make a rough prediction based on, viscosity, what kind of intermolecular forces, or if you know the intermolecular forces, you can kind of predict trends of viscosity or what you'd expect to happen with viscosity. And so here's just a list. You can look up a table in your book or a table in the CRC manual, and it'll essentially say someone has measured viscosity of various different things. And you'll see a general trend where the stronger the intermolecular forces, the higher the viscosity. Likewise, the longer the molecule, the higher the viscosity, so on and so forth. One thing to note again is that it's a temperature-dependent phenomena. So if you're ever going to talk about viscosity or compare viscosities, you have to note the temperature. It's not fair to compare honey at 200 degrees versus water at, approaching 0 degrees. And so you have to have apples to apples comparison. It is a temperature dependent phenomenon. So any of these tables will give you a temperature associated with these viscosities. All right, moving on to surface tension. And so surface tension has roughly the same idea. It's not pouring a solution, but it's instead basically the tension at the surface of a given liquid. And so you could think about this as the hardness of the liquid surface. And so the formal way to measure this is actually the energy required to increase the surface of a liquid. Basically, you're applying a force, and how much force do you have to apply to get that surface to change. And so You basically have intermolecular forces in the bulk of your solution, but you also have intermolecular forces at the surface. And so at this air-liquid interface, or this gas interface or vacuum interface, you're going to have these molecules wanting to interact with each other very strongly, or typically very strongly. And so they have nothing to interact with up here, and so they can only interact with each other. And the strength of that interaction is what's going to dictate the surface tension of that solution. And so again, we're talking about intermolecular forces, not resistance to flow, but instead how strong do these molecules interact and resist forces at that interface. And so just as we saw previously with viscosity, stronger intermolecular forces give you a higher surface tension, like it would physically hurt more to impact on something that has higher intermolecular forces. And again, this is a temperature-dependent phenomena. And so as the temperature increases, you start breaking those intermolecular forces, your surface tension will go down. And so it's easier to dive in warm water than it is cold water because the surface tension decreases with temperature. And so interestingly, they have a general rule with cliff diving where you're not supposed to dive when it's less than 12 degrees C because the surface tension is going to be much higher and you're more likely to get injured. So learned that factoid fairly recently. Just like viscosity, molecular size matters, intermolecular forces matter. The bigger the molecule, the greater the intermolecular forces, the higher the surface tension. Again, you can think about gasoline versus wax. Gasoline is a liquid. Wax is going to be a solid. It's a little bit mobile, but it's for the most part a solid at room temperature. And so obviously diving into wax would hurt a lot more than gasoline. And so just like you can with viscosity, you can look up these numbers in a table. In fact, this is a table that shows a bunch of different molecules, a bunch of different molecular formulas, their weight, their density, and then here's surface tension, and then here's viscosity. And so you can actually look up these values. And again, you have to report it at a particular temperature. But the take-home message for you guys is as intermolecular forces increase, surface tension increases. And it's because they're holding together much stronger at that interface. All right, so we did viscosity, we did surface tension, we covered the properties of the liquids. There's other things like capillary action, which we won't cover in this class, but when you start thinking about the properties of liquids in terms of how the molecules interact, it'll help you start rationalizing why they behave the way they do. And so having completed properties of liquids, now we're going to go on to phase transitions. And so harkening back to elementary or intermediate school science classes, you guys have all heard of gas, liquid, and solids, right? Solids are immobile, they're rigid at room temperature. Liquids, it can flow, it can occupy the volume of a container. Gases occupy a gaseous space. And so you know the different phases exist. You also have probably used this terminology regularly, the transitions between them. A solid going to liquid is melting. A liquid going to solid is freezing. Likewise, liquid going to gas, that's evaporation, and then gas going to liquid, that's condensation. And so there's real-world examples of all these phenomena. Less common language is solid going to gas, which is known as sublimation, and then gas going to solid, which is a deposition process. And we'll talk about a few examples of that in a little bit. But the main take-home for this is when you're talking about these transitions, you're effectively talking about breaking intermolecular interactions. And so what it takes to go from a solid to a liquid to gas, or to go from solid to gas directly, is you have to pump energy into the system. And the reason you're doing that is you have to break these interactions to go solid to liquid, break these interactions to go from liquid to gas. And so you have to pump energy into the system. You have to do that through increasing temperature. And so again, this energy is used to break those intermolecular forces. Likewise, if you go the other way, from gas to liquid to solid, you're releasing energy. And so as you condense a gas from a gas to a liquid, you're releasing energy. And so you're generating heat during that process. Same with a liquid going to a solid. That's why we put things in the freezer. We put it in a cold environment and seep that heat out of the system, and you can transition from a liquid to a solid. And so the inverse is happening. And so when you go this opposite direction, energy is being released when you're forming these intermolecular forces. Essentially, you're making a bond between these, an intermolecular bond, and it's releasing energy during that process. So energy goes in to go this way, energy comes out when you go this way. And so we'll just, for the remainder of the chapter, we'll just go through, a transition between liquid and gas, solid and liquid, and then solid and gas. And then we'll talk about a phase diagram, which is a summative depiction of all these various different transitions. So when talking about a liquid going to a gas, we have to talk about kinetic energy. And so this is essentially a physics problem. Energy equals 1/2 mass times velocity squared. And so you have a certain mass associated with your molecules or atoms, and they're going at a certain speed. But what's interesting about this is not all of them are going the same speed. And so if you had a jar of atoms and you could pick out one at a time and measure how fast it's going, you could make a graph that looks something like this. And so on this axis here is kinetic energy. That's essentially 1/2 mass times velocity squared. And then over here we have number of molecules. And so we're just going to count them one at a time, and we're going to make a histogram of the speed of these molecules. And so you pick out one, and it might be going slow, right? Slow molecules are over here on this side of the x-axis, and then fast molecules are over here. And so you had a slow molecule, you pick out a different one, it's going much faster. You pick out another one, it's somewhere in between. And so you can do this over and over again, and eventually you're going to build up a histogram that looks like this. And so this is a really common graph. It's called a Boltzmann distribution. But what it basically says is you have this distribution of molecular speeds at a given temperature, and it's going to look something like this. And so there's your graph right there. And so kinetic energy is here, slow molecules here, fast molecules here. Most of the molecules are going this speed, somewhere in this range. Some molecules are going really, really slow. Some molecules are going really, really fast. And what's important for this liquid to gas transition is the molecules that are going really slow are perfectly content to hang out here in the liquid phase. But every once in a while, you're going to get one molecule going so fast that it actually escapes from that liquid solution. Essentially, it has enough energy that it's overcoming those intermolecular forces, and it gets ejected into the headspace. And so those really fast molecules have achieved a speed where they can exit from that solution. You can think of it as like the molecular equivalent of escape velocity, where a rocket needs certain speed to leave Earth's orbit. Something similar here, where a molecule needs certain speed to leave the attraction of these molecules in solution. And so that's going to happen a bunch. You know, some molecules are going to have enough speed to go out into the gas phase, and then eventually in the gas phase, some of those are going to slow down enough, they're going to actually go back into solution. And so if you wait long enough, eventually you're going to reach this condition where the number of molecules leaving and the number of molecules entering is equal. And so you could look at this as the rate of evaporation equal the rate of condensation, or we'll get to it later, but this is an equilibrium condition. Basically, you know, individual molecules are moving back and forth, but overall, you're going to have a balance between a certain number of molecules in the gas phase and a certain number here in the liquid phase, and that is going to be your vapor pressure. And so molecules over a certain threshold escape, molecules go slow down and come back down. And so again, that's known as the vapor pressure. It's basically the pressure generated by the molecules that had sufficient energy to leave the liquid phase and go into the gas phase, and vice versa. And so yeah, that's what your vapor pressure is. And so the way we measure vapor pressure, we essentially have a hygrometer or a pressure meter of some kind, that these molecules that are up here in the gas phase are exerting force on the container. And they can exert so much force by bouncing against the walls that they can actually apply pressure, and you can measure that pressure. And so the classic way to do this is with a mercury tube like this, and then you can actually measure the pressure in the form of millimeter of mercury difference between these two heights. It's basically how much force is applied here versus atmospheric or vacuum on the other side. And so that's how we can measure that pressure, that vapor pressure from a solution. And so, yeah, the formal definition of vapor pressure is the pressure exerted by a vapor in equilibrium with its condensed phase. So again, this idea of molecules coming out of solution and going out in the gas phase. And molecules in equal molecules out. Rate of evaporation equal the rate of the condensation in a closed system. This is important because if this isn't closed, these molecules just go wherever they want and they don't exert pressure here. They're just going to escape. But in a closed system, the number of molecules in equals the number of molecules out, and you have a vapor pressure. And so just like everything we talked about previously when we're talking about the property of liquids, these are going to be primarily dictated by intermolecular forces. How easy is it for a molecule to reach that escape velocity? How much speed does it have to get out of that solution? The lower the intermolecular forces, or the weaker, the easier it is going to be to happen. However, the stronger those intermolecular forces, the less likely it is to enter the gas phase, and the lower that vapor pressure is going to be. And just like previously discussed, it's going to be temperature dependent, right? The more you heat it up, the more it's going to break those intermolecular forces, the more things are going to speed up, and the more they can escape that solution and give you a higher vapor pressure. And so, actually this is wrong. This should be temperatures up, intermolecular forces down, vapor pressure should go up. And so that should be an up arrow. But by how much is the question. And so when we talked about that kinetic energy of molecules in solution, what we're effectively talking about is a measure of temperature. That is, after all, that's what temperature is. Like, we think about it as an abstract number, but really it's a representation of the average kinetic energy of molecules in any given system. And so here's our histogram again, kinetic energy versus fraction of molecules at a given kinetic energy. It's this histogram we saw earlier. At lower temperature, molecules are going slower on average. At higher temperature, molecules are going faster on average. And so in both temperatures, you have some really fast, some really slow. It's just a question of what the bulk behavior is. Is it mostly slower and mostly faster? Temperature dictates that. And so at lower temperature, most are going slower. At higher temperature, more are going faster. And so we talked about this idea of escape velocity, or a threshold where molecules can start exiting solution. Well, you're going to have some energy threshold, and that energy threshold will be the same no matter what temperature it is. It's just as soon as you reach that much energy, you can break those intermolecular forces and you can escape. The difference between high and low temperature is not that threshold, but instead how many molecules are over that threshold. And so if it's low temperature, you have less fast molecules, this blue region down here. If it's fast, you have higher or a larger number of molecules leaving that solution. And so you can think about this conceptually in terms of lower temperature, these molecules are moving much slower, and you're going to have a few escape, and then at higher temperature, they're going to be moving much faster. And so on average, there's going to be more of these that can escape than can escape from this solution. And so the vapor pressure here will be lower than the vapor pressure here. And so that's where the vapor pressure temperature dependence comes from. And so again, lower temperature, lower vapor pressure, less molecules in the gas phase. Higher temperature, higher vapor pressure, more molecules in the gas phase. And so there's your relationship. You can think about this as a stepwise process, but the higher the temperature, the higher the average kinetic energy, the faster those molecules are moving, the more fast molecules can escape the solution, and that gives you a higher vapor pressure. And so it's all tied together back to this idea of intermolecular forces. How fast are those molecules moving, and can they leave that solution? And so we can be more quantitative than that, right? We know that as, temperature goes up, the vapor pressure is going to go up. But what's the relationship between those variables? And so we could do this experiment right now. We could get a hot plate where we can control the temperature. We could have a closed system where we hook up a hygrometer, and we could essentially do a measurement, right? We could take it, fill the container with a liquid, set it at a certain temperature, measure the pressure. We could heat the plate up, measure it again, heat the plate up, measure it again, and we can make a graph that looks something like this. And so the x-axis here is temperature, the y-axis here is vapor pressure. And so as you can see with these two examples, there's diethyl ether and there's water. As the temperature goes up, the vapor pressure goes up. And that's exactly what we'd expect, right? It doesn't matter what the intermolecular forces are, at least in terms of its intrinsic relationship, is as the temperature goes up, the vapor pressure increases. As the temperature goes up, vapor pressure increases. And so we can take this data and we can graph it in a slightly different way. If we do natural log of p, so this is just like taking an Excel spreadsheet where you have an x and a y. If you take 1 over x and natural log of y and you graph those two together, you get a graph that looks like this. And so here you can see water, H2O, is this line right here, and then your diethyl ether is this line right here. And so what's really important about straight lines, and we talked about this previously, is it has a lot of predictive capacity. Not only that, but straight lines give us this relationship, y equals mx plus b. And so we have a relationship between the x-axis and the y-axis, and we have a y-intercept, which is b, and we have m, which is the slope of that line. And so if you know this equation, you can draw this line, you can predict any relationship between x and y axes. And so for this particular relationship of temperature and vapor pressure, we have this form of the y equals mx plus b equation, which is also known as the Clausius-Clapeyron equation. And so in this case, natural log of p, that's your y-axis, 1 over t, that's your x-axis, plus c is a constant, that's the y-intercept, and then your slope of the line is negative delta h vap over r. And so this r is a gas constant, that's always constant. Your two variables are t and p and the relationship between them. And then ultimately the slope is dictated by this delta h vap. And this delta h vap is the molar heat of vaporization. And so what this molar heat of vaporization effectively is, and here's the formal definition, it's the energy required to vaporize 1 mole of liquid at its boiling point. So it basically says at the boiling temperature, whatever that is, how much energy do you have to pump in the system to break those intermolecular forces and shoot those molecules up into the gas phase? And so this is an intrinsic descriptor of the material. And so this value is temperature independent, right? Temperature dictates how much energy you pump in, but this delta H vap is basically the threshold energy necessary to vaporize a mole. And so it's basically, it's a physical descriptor of intermolecular forces. That's where those numbers come from, right? The energy necessary to break bonds. In this case, it's the energy necessary to turn something from a liquid into a gas phase. And so that's where we get this relationship, right? Temperature and pressure is going to be dictated by that delta H vap or the intermolecular forces. And so you can see from the equation, if this delta H vap goes up, basically it takes more energy to break those intermolecular forces, your pressure is going to go down. And so you can see this proportionality formed two different ways. Natural log P is proportional to the negative delta H vap, or P is proportional E to the negative delta H vap. It basically says there's this inverse relationship between those two. As delta H vap goes down, up, P goes down, and vice versa. You also have a temperature-pressure relationship here, right? And so as the temperature goes up, the pressure goes up, and that's exactly what you see in the equation, right? Natural log of P is proportional to negative 1 over T. This one's a little confusing because there's a negative sign and an inverse, and so the bigger the T gets, the smaller this number that gets, the less negative it becomes. But yeah, work through that in your head. The relationship works out. And so again, that's where this graph effectively comes from. It says there's a relationship between temperature and pressure, and delta H vap is dictating where that relationship shows up on this graph. And so if you had to look at how it dictates this curve, basically if you have a lower delta H vap, you're going to have a lower or a higher pressure, and that's exactly what you see here. Diethyl ether is going to have a higher vapor pressure than water at a given temperature, and it's because the intermolecular forces for diethyl ether are weaker than for water. And so it's because diethyl ether is dipole-dipole, water is hydrogen bonding. And so that delta H vap dictates where this pressure temperature curve is going to show up on this graph. And so to reiterate, no matter what liquid you're dealing with, there's a temperature-pressure relationship. The where that relationship shows up is going to be dictated by the delta H vap, the intermolecular forces, and how strong or weak they are. And so, tying it back to our starting point, the greater the intermolecular forces, the greater the delta H vap, the lower the vapor pressure is going to be for the system. So we can draw this equation in a slightly different way. So the slope is effectively the change in y over the change in x, right? And that's just standard linear algebra relationship. What's convenient about that is effectively if we know any point on this curve, we can predict another point, right? And so that's what these two forms of the Clausius-Clapeyron equation effectively do. You have P1, T1, you have P2, T2. So you have temperature 1, pressure 1, temperature 2, pressure 2. If you know 2 points, you can draw the straight line and figure out the delta H vap over R. If you know delta H vap and you know one starting point, you can predict any other point with respect to X or Y. And so that's why it's really useful. It lets you predict temperature and pressure. And this can be really important on an industrial scale where you may increase the temperature of the reaction over a pressure threshold where it can no longer handle the reaction. So yeah, if you know these values, you can predict other things. Again, that's ultimately what we want to do. We want to understand it well enough to predict what's going to happen. All right, so everything we've talked about so far is a closed system, right? And closed system means those molecules can't go anywhere. They can't escape from the system. There's a equilibrium between molecules evaporating and molecules condensing, and that effectively gives you the vapor pressure. Now, if you do an open system, that completely breaks that vapor pressure relationship because molecules go out, but mostly they don't go back in. And so it's not at equilibrium. There is vapor pressure, but it's not an equilibrium condition. Those molecules are effectively lost to the system. But in this open system, this is where we get boiling. Essentially, a closed system, you don't see boiling. I mean, you can, but it's not dictated by external pressure. But there's a relationship between the external pressure and the vapor pressure of a system, and that's what dictates the boiling point. And so take an example where we have a a system that has a low vapor pressure at a low temperature, right? And so we have some vapor pressure of molecules exerting force on the external environment, and then we have an external pressure that's dictated by our atmosphere, which in our case at sea level is 1 atmosphere of pressure. Now, if we heat up this solution, we're going to increase the vapor pressure, right? We're going to increase the vapor pressure so much that a lot of molecules are going to start escaping. A lot of them are going to have that escape velocity, and it's going to reach a threshold where your vapor pressure is the same or greater than your external pressure. And when that happens, you have reached the boiling point of the solution. And so prior to this relationship where external pressure equals vapor pressure, it's not going to boil. But as soon as you reach that threshold, all of a sudden you're going to start generating gas molecules that's where bubbles come from. It's gas molecules of whatever liquid it is, and they're going to have enough force to overcome the external pressure. And that's where the boiling effectively comes from. And so the thing, again, this is, people want to say that the bubbles are made of air. They're not made of air. It's actually vapor water molecules. If you're boiling water, it's not air bubbles being created. It's literally water vapor. And so you're making gas water molecules inside the liquid solution, and they're going to go up to the surface and they're going to pop and they're going to go up into the gas phase. That's what's happening when a system boils. And so that threshold is called your boiling point. That's where the boiling point comes from. It's the temperature at which the liquid's vapor pressure is equal to the applied external pressure. And so your vapor pressure overcomes external pressure. Those molecules go up into the gas phase and explode. We also have another formal definition called the normal boiling point. And so this boiling point, since vapor pressure is temperature dependent, your boiling point is also temperature dependent, but we say, external pressure dependent. And so we have a normal boiling point that's effectively what is the boiling point when the external pressure is 1 atmosphere. And so we fix the external pressure. That gives us a normal boiling point, but you can have a boiling point at any given pressure. And so again, the idea behind normal boiling point or a boiling point at all is that the external pressure matters, and that's what dictates your boiling point. And so you get graphs that look something like this. And so we have vapor pressure versus temperature. And we saw this curve earlier, but this graph also tells you where the boiling point is going to be at a given pressure. And so remember, as soon as the vapor pressure equals external pressure, it's going to boil. And so if you take a standard external pressure of 1 atmosphere on this graph, you can draw a line over here, you can draw a line here. It tells you the boiling point is 100 degrees C. If you cut that external pressure in half, 0.5 atmospheres, let's say you climb up a mountain and you reduce the external pressure, it's going to change your boiling point. It's going to lower the vapor pressure, or lower the threshold necessary for vapor pressure to reach external pressure, and then all of a sudden the boiling point becomes 81 degrees C. Likewise, you could increase the pressure to 4 atmospheres if you're in a submarine or bottom of the ocean. The boiling point increases to 144 degrees C. And it's just the external pressure is what dictates when it's going to boil, and your vapor pressure has to equal that external pressure, and it happens at 144 degrees C. And so that's the relationship between pressure and boiling point. All right, so we've talked about liquid to gases a whole bunch. There's also solid-liquid transitions. And so when we talked about the gas-liquid transition, we talked about the molar heat of vaporization, this delta H vap, energy required to vaporize 1 mole of liquid to gas. There's an equivalent descriptor for liquid to solid transition, which is known as the molar heat of fusion. It's not as intuitive because we're not talking about temperature-pressure relationships. In this case, we're talking about the energy required to melt 1 mole of solid, and also the energy released when 1 mole of liquid is frozen. And so it's the same idea. You have these interactions in the solid state. You need to break up those interactions and increase the mobility of those molecules. This tells you how much energy it takes to make that happen, or how much energy is released when it goes from a liquid to a solid. And so very similar concept to the molar heat of vaporization, but this is the molar heat of fusion. And so if you go to your data tables or the appendix at the back of the book, you can look up these values. Just as you can find tables of molar heat of vaporization, you can find molar heat of fusion, and you can see for different substances you're going to get molar heat of fusion. And again, it's going to depend on how those things interact. You also have things like lattice energies and other things that happen in the solid state that's not in a liquid or gas phase. We can do something similar for the gas-solid transition or the solid-gas transition. And so we have sublimation, where we go directly from a solid to a gas. This one, believe it or not, you do have experience with it. Not necessarily with iodide. It's a really common chemical that's known to go to the gas phase. But something as simple as freezer burn. Freezer burn, or your ice cubes disappearing in your freezer, is effectively a vapor pressure associated with ice cubes. They're solid, but there are gas molecules escaping, and over time these ice cubes shrink because enough gas molecules are disappearing. You can go the other way. You can deposit or deposition, go from a gas to a solid. This is essentially, you had molecules in the gas phase, they're cooling down enough where they're going to go to a solid state. It's a solid gas equilibrium in that case. And so we're in Florida, but icy windshields is a byproduct of this. You have enough water in the air, but it cools down enough that you start depositing that atmospheric gaseous water in the form of ice on your windshield. And so that's a gas to solid transition. Similarly, if you have a fireplace, the soot or the black carbon that ends up building around the fireplace, that's a gas phase deposition process. And so the fire burns, you get carbon shot up into the atmosphere in the gas phase. It cools down enough where it's going to deposit on a surface, and that's where their black soot comes from. And so we had this descriptor, molar heat of vaporization, the energy required to vaporize 1 mole of liquid to gas, molar heat of fusion, energy required to melt 1 mole of solid. We can also define a molar heat of sublimation. Basically, how much energy does it take to go from solid to gas? How much energy is released when it goes from gas to solid? And it's basically the sum of these two. And so in Gen Chem 1, you learned about Hess's law. Thermodynamic functions don't care how you get there. If you sum up molar heat of fusion, molar heat of vaporization, you get a molar heat of sublimation, which is basically how much energy does it take to go directly from a solid to a gas, or how much is released when gas goes directly to solid. And so summarizing a lot of the things we've talked about so far, we have this heating curve, or a phase change in heating curve. And so this basically is a relationship between heat added to the system and the temperature of that system. And so as you go further to the right, you're adding more and more heat to the system. And so let's start out at point A, where we have like ice, right? Some kind of solid. In this case, it's the water phase change in heating curve. But you could do this with any solid. So as you increase the temperature, or increase the amount of heat you add to the system, that heat goes to moving molecules faster and faster. And so you can see the temperature goes up, the temperature goes up, temperature goes up, and then it's going to reach a certain threshold. And at that threshold, all that energy that you're pumping into the system, it no longer goes into moving molecules faster and faster. Instead, that energy goes to breaking intermolecular forces. And so that's where you have a phase change. And so here we had ice. We're effectively moving that ice faster and faster. It's still ice. It's not liquid yet. It's still ice, but it's moving faster and faster. And then it reaches a threshold where that ice is going to turn to liquid, and the temperature is not going to change because we're not making molecules move faster. Instead, we're making molecules break those intermolecular forces and change phase from an ice to a liquid. And so this red line right here is melting. And then we can keep heating, and eventually all the solid is gone. And so at this threshold C, we're to entirely liquid water. And we put energy into that liquid water, pump energy in, pump energy in. All that energy is going to make those liquid water molecules move faster and faster. And as a result, the temperature is increasing, temperature is going to increase. And then we're going to reach a threshold, right? And this is the threshold right here. This is effectively the boiling point at 1 atmosphere of pressure. At 100 degrees C, those water molecules are moving fast enough that they can escape the solution and go into the gas phase. And so all that energy that we pump into those molecules is to break those intermolecular forces and eject those molecules into the vapor phase. And eventually all the liquid's gone, and now we're just water vapor. And we can heat up water vapor. It'll keep going faster and faster. That's what steam cleaners do. They're pressurized chambers that you heat up more and more. You can make those vapor molecules move faster and faster and be hotter and hotter. And eventually you'll reach a phase where it's not even gas anymore. It becomes something else. And so yeah, this curve of heat added versus these phase transitions in temperature really is a culmination of all these types of interactions occurring. Something important to note is that the shape of this curve, or the position of this curve, will change depending on the intermolecular forces. It'll dictate how much energy it takes to break these interactions here and here. The size of the molecules will dictate how fast they speed up as you dump energy into the system. And so, yeah, that's our summary. We have intermolecular forces dictating, viscosity as well as surface tension and vapor pressure. We have these phases, solid, liquid, gas, and we have the transition between those phases. It's entirely dictated by these intermolecular forces and how you have to break them and make those transitions happen. And so, again, going into this journey, we have a molecular formula. We draw a 3D structure. We assign the molecule as polar, nonpolar, or ionic. We assign the intermolecular forces. We can estimate the relative strengths of those intermolecular forces, and we can predict properties, or at least trends in properties. We can look at a molecule and say, this is probably going to have a higher vapor pressure than this because it has weaker intermolecular forces. And that's ultimately the goal with understanding these interactions. So yeah, that closes out our properties of liquids and phase transitions. Next, we'll start talking about phase diagrams.